everyone to this special Dean's Distinguished Lecture, which is hosted by the Department of Combinatorics and Optimization and is also their Distinguished Thought Lecture. My name is Christiane Lemieux. I'm the Associate Dean Operations and Academic for the Faculty of Math. Normally, as the name of this series suggests, the Dean would be here to do the introduction, but he's on a different continent today, so couldn't be here and join this event. So you're going to have me instead. I don't want to take too much of your time. I'm sure you're eager to hear from our distinguished speaker today. But I did want to start by acknowledging that we're gathered here today on the traditional territory of the neutral Anishinaabe and Haudenosaunee people. The University of Waterloo is situated on the Alderman Tract, which is the land that was granted to the Six Nations and includes 6 miles on each side of the Grand River. So doing this territorial acknowledgement is an important step, but maybe more importantly, there is active work happening on campus toward reconciliation, and it's coordinated by our Office of Indigenous Relations. So today's distinguished talk is a joint effort between the Department of Combinatorics and Optimization and our Women in Math group, who is led by our Professor Yuru Liu from the Department of Pure Math. And so Yuru wanted me to say a few words on behalf of WIM. So first of all, that this Dean's Distinguished Lecture Series is something that originated from something that used to be called a WIM Colloquium. But it's a little bit different now, and it's actually quite different. And one of the big differences is that WIM is working with the research units to identify an excellent speaker. And today's event is a proof that this was a great direction for WIM to take with this Distinguished Lecture Series. So on behalf of WIM, we're grateful for the Department of CNO to be collaborating on this event today. So without further ado, I will pass it over to Professor Douglas Stabila, who's going to introduce our distinguished speaker.
Thanks, Christiane. So I'm very pleased today to introduce to you our distinguished lecturer, Tal Rabin. Tal is a senior principal scientist at Amazon Web Services and a professor of computer science at the University of Pennsylvania. She has had a long and distinguished career in cryptography, setting the stage for the fields of multiparty computation and threshold cryptography, which she'll be talking about today, and helping bring them from just a twinkle in her and her colleagues' eyes to a really important field of active work that is seeing adoption. Tal spent 20 years at IBM Research and also at Algorand. She's the winner of many awards. She's a fellow of the Association for Computing Machinery and the International Association for Cryptologic Research, as well as a member of the American Academy of Arts and Sciences, and a winner of a Test of Time award from Stock. She's been very active in our community, and among the many things that she's done to build the community is acting as the founder of a Women in Theory workshop series, which has been an important opportunity for many people in the field. So thank you, Tal, for joining us today. After the talk, please come and join us for a reception across the way. But for now, thank you, Tal.
So I changed my title a little bit because I decided that I also wanted to talk about threshold cryptography. We'll go through all these things and see what they are. So multiparty computations was introduced in 1982 by Yao with a very, very simple question. 2 millionaires want to know who's richer. Just that simple question. Of course, there's a very trivial solution to the problem. You know, I'll say I have $10, he'll say he has $15, and we'll know that he's richer. But this was not the point of the question. The question was, without finding any additional information about the inputs of the party, that he doesn't learn that I have $10 and I don't learn that he has $15, we only learn that he's richer. And the question was whether you can solve this problem and give a solution to this thing. Of course, today, nobody will be talking about millionaires and then $10 and $15. It'll all be billionaires. And basically, it's not just two parties. You can think about it, three parties or even more. Each one has an input. And in fact, it doesn't even have to be who's the richest. It could be any function of their inputs, of x1, x2, and x3. So we want to say anything, any function that you can compute without learning anything about the inputs, preserving the privacy of the inputs. So this is sort of a generalization. And if we generalize it further, it would just be that we have n parties. They have their inputs respectfully, and they want to compute the function without learning anything. And we make things a little harder, and we say that some of the parties can be faulty, okay? They will not follow the protocol. This, of course, immediately you can say, okay, if he puts the number 9 into the computation, I can't do anything about that, and it ruins the computation. But under the assumption that people put in their real inputs to the computation, but then try to learn as much as they can, or to sabotage the computation, we still want the computation to go through. And we can do this under various restrictions and limitations on these things. So when Yao introduced this problem, he also gave a solution, and he gave a solution in the computational setting. What does the computational setting mean? In cryptography, we have all kinds of primitives, like encryption, signatures. You use these things all the time on your phones, on your computers, and so on. But these cryptographic schemes are based on some assumption, some computational assumption. For example, we assume that factoring large composites that are a product of two primes is hard to do. Not because we don't have an algorithm. You all learned this algorithm probably in 7th grade. We know how to factor numbers. But to factor it efficiently, we assume is hard. When we go to large numbers, we say this is hard. So under such computational assumptions, Yao presented a protocol that achieves multi-party computations. And in fact, it said, it's a theorem we can compute anything, any function that is given, we can compute. So were we done? Was Yao's solution the end it all? I can tell you 82 to now is 40 years. The number of papers that have been written in the area of multi-party computations, clearly it was not the end. But it was not the end, not just because you can always do more, but we also thought maybe we could get rid of the computational assumption. So, as I said, Yao's solution was based on factoring or discrete log. These are equivalent, and these are things that we definitely know that we can break once there is a quantum computer. Maybe we don't believe a quantum computer will exist in the X number of years going into the future, but still it's good to do things differently. So, in case it's broken, we want to try and do these computations in a different way. And what would we want to do? We'd want to offer a solution that does not make any computational assumptions, that it'll be secure even if the adversary is computationally unbounded. Because these schemes that I told you, factoring, of course, if the adversary is not bounded, it'll work until it factors, which we said we know how to do. So when we started working on this in the late 80s, it was an interesting theoretical question. And not all research has to be driven I forgot the word. I have it in Hebrew, but sometimes it doesn't translate. Okay. Driven by actual applications that you want to do. Sometimes we look at things also just for their beauty and so on. Math for many, many areas, that's definitely the case. also in theoretical computer science. And this sort of arose at the end of the 80s as an interesting question. Can we do it just with no computational assumption? So we really looked at it in that sort of viewpoint. But it turns out later that it really is nice to try and give a solution in the information theoretical model, because we later learned that there was these ways that you could factor numbers if you had a quantum computer. But if your solution is information theoretically secure, it doesn't matter if a quantum computer will be built, because you can still maintain the security of the protocol under these things. And also, we learned that it's also efficient. And it has low computational costs, and we could do things better. In the computational setting, we had to work with bits. Here we could do arithmetic circuits and so on. So it turned out that the information theoretic setting had a lot of advantages. And it turned out that these solutions that used information theoretic constructions were used for many, many things, like in PCP and many things. Don't know what this, doesn't matter. We could really utilize it in a very, very broad way. And today we have solutions that are information theoretically secure that are very, very efficient. Okay, so what about multiparty computations? As I told you, Yao's paper was 40 years ago, and we've had a lot of work about these things, around these topics. And we believe that these multiparty computations really have a use now in practice. I said we started off thinking about it theoretically, but today we think that there is really actual use for these techniques. And I'll give you a few examples where you can deploy multiparty computations. You want to do a bid in an auction house, but people don't want to expose their bids. Today, you know, you raise your paddle, everybody sees how much you're bidding. But maybe you want to keep your bid secure, secret. So if you had a multiparty computation, we all could enter our bids. We'd run a multiparty computation, and the answer that we would get is that she's the winner. Her bid will be exposed because she's the highest bidder. Maybe we do a second value auction, it'll be the second value. We will learn that, but everyone else's bids will remain secret. So here's a great application of multiparty computations. Here's another great application, voting. We want to vote, we want the elections to be secure in some way. This could enable us to vote over the internet. We all enter our vote into this multi-party computation box, let's call it a box. And what comes out is the winner of the election. Hopefully it's somebody we like, many times it isn't. So we use these techniques to do voting, distributed voting, while preserving the privacy. Here's another issue. You want to do research about data of patients. This data many times needs to be secure and private. You cannot share it. But there are two hospitals that have a person with a very, very unique disease. You need the combined information in order to derive any leverage from this thing, but they can't share. But if they do a multi-party computation, maybe they want to find something specific about the disease, they get only that answer out without exposing all the input of the single patient. So you can do that. Another thing which has become very popular, and this is what I added with the threshold, and I'll discuss this as well. For many cryptographic schemes, you have a secret key for signing and for encryption. And cryptocurrency wallets use digital signatures in order to give the instruction to buy or to sell. So this secret key of your wallet is what holds your tokens. If you lose your secret key, you've lost your tokens. If you're lucky and you have 10 Bitcoins, you really don't want to lose that key, because whoever has the key is going to sell your 10 tokens and have $670,000. So you want to secure this key. And the way that you can secure this key, you can think about it as a multi-party computation, okay? You take this key and you break it up. You put a piece here and a piece here. And you do a computation that generates the signature, okay? But the two pieces, it ensures that the two pieces, you don't learn anything about the inputs, right? So you can utilize this scheme in order to enhance the security of your wallet. And this is, in fact, a technique that could be used. By the way, if you have any questions, just barge in. Okay. But in practice, not a lot is happening, which is somewhat distressing. And, not totally depressing, but you would want these things to somehow be adopted and utilized, especially when you believe that they do bring value. So, as I mentioned before, on one of these examples, which was the medical one, it looks like we're going to be getting some help from legislation. Privacy legislation around the world is on the rise, and they really prevent data being shared. And hopefully, these requirements that the governments are imposing will drive the adoption of multi-party computations. And I'll give you a few examples of where it can be. So MPC to the rescue, we can do it, because I want to say, I said about Yao, that Yao said we can compute any function. Also, the information theoretic solutions say we can compute any function. So really, we know how to do anything that is needed. But there are challenges, and I'll tell you what the challenges are, and why there is really here an opportunity for much more work and much more research to be done on this front. Yao's solution, and I mentioned here a few more, and our solutions later, they say that we can solve the problem. We know that we have a solution, but it's a very generic solution. And generic solutions don't always provide the most efficient and really practical way to solve the problem. Sometimes the fact that we can do it, okay, let's say if we had a voting algorithm that if we use a generic technique would give us the answer in a year, nobody would want to do it. Or the hospital solution, if it would take a month and this patient is really in bad condition, you don't want these things to take a long time. So the generic solutions are not fast enough. So there is really here an opportunity to build dedicated solutions. If you find an interesting problem that somebody wants to solve, you can design for them something that works much faster. I'll give an example of something that we did that relates to this as well. Another challenge is that these solutions today need to be designed by experts. These dedicated multi-party computation solutions, or FHE solutions, which is another technique for doing these things, they have to be designed by cryptographers, which not everybody can have a cryptographer. There aren't enough of us all around to design all the problems that are needed. So I'll discuss a little bit about this later on of what we do, but basically we have to find an issue to this thing that we currently need experts to deal with it. And of course, there are also proliferation of models which are a challenge. And what I mean by models, for example, computational, not computational. Is the system synchronous or asynchronous? Are the parties participating? Will they follow the protocol, or will they be malicious and try to hurt and so on? And when you go and design a protocol for a specific problem, you really have to figure out first what your model is. What is the specific setting that this protocol will be running in? And you would need to go and then provide a solution in that model. Okay. So, as I said, great opportunities ahead, and I want to give you a few examples. Ads. So ads, I don't know how much you're aware of today, but ads basically are, and browsers basically are tracking everything you do. I don't know what your level of awareness is, but there's third-party cookies, and basically when you go here, they know you've been there, and so on and so forth. And through Apple's pushing, third-party cookies are going to be deprecated. Who knows when, but it's happening, it's coming. But people still want, let's say, advertisers who do a campaign. They still want to know, how many people has this campaign reached? What was its effectiveness? How many people clicked after they saw the ad? They need this information in order to pursue their business. They can't have it now with a name. They can't know that Douglas was the one who had looked at the ad because the third-party cookies are going to be gone. But maybe aggregate statistics would be good enough for them. Let's say they do a campaign. They know that it reached 500,000 people. Something like that, they're still willing to settle for. So in fact, there is an organization, the World Federation of Advertisers, who put in a working group in place exactly to design multi-party computations that will give them this information, specifically reach, which is how many people it reached, and frequency, how many people saw the ad 3 times, 4 times, and so on. And a dedicated multi-party computation was designed for this organization to solve this problem. So maybe this problem is solved, but there are many, many more like these that need to be solved. Again, the medical example that I told you about before, these are endless questions, and every medical research needs something else computed. So you can look at things like that as well. And now we have machine learning, the answer to everything. So machine learning also have settings where they want to do computations, but to keep the information private. Here is a setting. There is a server, let's say a bank, and it has many, many clients. And it wants to compute some model of the client's activities. The clients don't want to share this information in full. But they are willing to participate in a computation, which is called a federated learning, that somehow the server will get an aggregation of all their inputs, let's say the sum, okay? So there's room here to design a multi-party computation. That's exactly what you need, just that all the parties will input their information and somehow the sum will pop out. Speaking about models, I want to say something about this model, which I didn't say before about models. This is a model. Think of a bank, how many clients it has. It has millions of clients. So here is a case where we need to do a multi-party computation where the model is such that there are many, many, many parties. And how do you solve that problem? To offer the sum of these inputs so that the server learns nothing but the sum, and it's efficient enough. Many of the multi-party computations have an n-square communication. There are n parties, the communication would be n squared. You can see that if you're in a setting with 1,000,000 parties, you can't do n squared. So you have to find a special solution that will work in this model. Okay, and again, the cryptocurrency, this is actually something that is active, and there are companies that are that exist and are trying to offer threshold signatures for individuals and for big companies that hold a lot of cryptocurrency. Okay. And I said that I would give you a special example. This is something that we had done. There is some people in the University of Urbana who put a competition in place, which is called IDASH. And what they do is they propose medical problems that they ask that there be a private protocol, an MPC protocol, or an FHE protocol, I didn't discuss FHE, that solves this problem in a reasonable time. And the problem here that they proposed, you have to follow exactly what they say that the problem is. There was a DNA database held by the hospital. The hospital could not share this database. And it had genomic descriptions of patients and the disease that that patient had. Okay? Now, there was a doctor who had a patient who was sick, but they didn't know what the patient had, and they had also sequenced the patient's DNA. And the goal of the problem was that the doctor would run in the MPC. The doctor would provide the DNA sample. The hospital would provide the database. And the doctor would receive the diseases of the 7 closest patients that the DNA was the closest. It would receive their diseases. And this was for the area where the disease was identified, okay? And you can see that this is a huge thing to match DNA sequences and to find the 7 that were closest. And we did a generic design at the beginning. We didn't really run it. We just calculated how long it would take, and I think it was over a month to get the answer. But we designed a protocol, and we were going to be measured on 2 things. We were going to be measured on the speed of the protocol and on the accuracy, because of course being fast is not that difficult, but you also have to give a good answer. So we did some pre-processing of the data, which took, I think, 2 minutes. And after that pre-processing of the data, we could give an answer in 2 seconds. And we were supposed to give the 7 closest. We always gave 7 from the top 9. So we were really quite accurate. And we won first place. There were people who were more accurate than us, who gave the full top 7, but they run much slower. And of course, there were people, nobody ran faster than us, but there were people who ran fast, but were much less accurate. So this was the thing. So you can see that you can design protocols for extremely complex computations with this multi-party computation. But we went into the specific function that we were computing, which was the Hamming distance between these things, and we analyzed it for that purpose. This MPC cannot compute anything else. It can only compute this function. Okay, so here's a little bit of the performance. There were 1,000 records. Oh, it was 6 seconds. I'm sorry that I said, okay, I didn't remember the numbers. It was 6 seconds to find the 5 closest. Okay, and you also have to think about the communication of how much bandwidth you need and so on. Okay, so I spoke to you and I showed you here that we have to really tailor the solutions. And that protocol, I think 4 cryptographers worked on, okay? This is a lot of specialized brain power that is needed to solve this problem. And we can't do it for everything. So the question is, can we do something else? And this is yet another place where there's huge opportunity for work and research and so on. Maybe each of the things here is some cryptographic primitive. Oblivious transfer, set intersection, secret sharing, and so on. Doesn't matter what they are. Maybe we can build a toolkit. And people are starting to try and do it. These things are being worked on, but they're still not where we'd want them to be. And when you would want to come and design a protocol, and you're not a cryptography expert, you could go to that toolkit and take these things, and there would be mechanisms for you to combine them to deliver the result. Maybe it won't be like our solution for the genome, that I don't know if it could be optimized more, maybe it could. Things can always maybe be better. But you'd be able to build something. We'd have a box of things, and you can take them, and it would reduce the level of expertise that is needed in order to design a protocol. And if we manage to do these things and to build the programming languages to sew everything together, then of course we would be increasing the number of people who can deliver multi-party computations, which of course would be a huge advantage. So this is also something that I think has a lot very difficult problems to solve here, but a lot of very interesting work to be done. And as I said, people are embarking on it, but we're nowhere close to have anything that really people can use. Okay, so now I wanted to give a flavor of multi-party computation ideas, but in fact, I had a more complex solution that utilizes polynomials. But I'm going to give a little bit of math, but I reduced the level because I think it's more enjoyable when you can fully understand the example, even if it's not really the way that it's done. But we'll do it this way. So again, to our general problem, we have n parties. They have inputs, and we want to compute a function. And the way that things were presented in Yao slightly differently, but in papers from 1988, which were the first that started with the multi-party computation in the information theoretic setting, they said, let's look at the function. It's basically a circuit. Additions and multiplications. With addition and multiplications, we can compute any function. So let's provide a mechanism to do an addition and a mechanism to do multiplication. Okay? And that these mechanisms would enable us to input the inputs in a way that preserve their privacy. And the computation of the gate, of the plus or the multiplication, would also preserve the privacy of the input. And that these inputs would be inserted in some format, and the output of the gate would be in the same format. Okay? And this way, we will propagate through the computation until we reach the end, and at the end, we will reconstruct the output of the function in some way. Just to give you a really high idea of how these things are done in actuality and not how I'm going to show them, this is done via distribution of values via polynomials. It's very easy to add polynomials. It's also easy to multiply polynomials, but it's a little bit more complex, and there are protocols that describe how to do it. But I'm really going to do it in a way that if you have a non-computer science friend, you can later go and explain to them this thing without a problem, even if they're not proficient in math. And I like this because when I first learned, I don't know if you guys know what it is, the notion of zero knowledge, which is really an amazing idea. It doesn't matter what it is. I told a friend of mine about it. And we were in our early 20s, so about 40 years ago. And to this day, he says to me, you know, it's the most amazing thing I've ever heard. So maybe multi-party computations will be this for you and your friends. Okay, so we have 3 parties for International Women's Day. And these 3 parties have 3 inputs. She has a 13, a 7, and a 21. And what we want to do is, as I said, we need to show how to do two operations. We need to show how to do an addition and how to do a multiplication. So I will show you how we do an addition while preserving the inputs of the party. Okay, so the goal is to compute the sum. I wrote for myself a cheat sheet for 41 because my addition abilities are very, very minimal. To create these slides took me a long, long time because I made so many mistakes. Okay, so we want to compute 41, and we want to preserve the privacy of the inputs. Okay? So let's look at what these three parties will do. She has the number 13. Okay? She will take and she'll split it into three values that sum up to 13. I'm doing it over the integers. You're really supposed to, for full privacy, to do it in a prime field. So this thing is equal 13. Okay? She just created these numbers. This one created these numbers, and that one created those numbers. Now, I want to say, how did she create these numbers, this first person? She chose a number at random, -6. She chose a number at random, 12, and then the 7 was forced by the 13, okay? I'm sure you clearly see why the -6 and the 12 reveal nothing about the 13, right? They were chosen at random. They clearly reveal nothing. But the truth of the matter is that neither does the 7, because this is also in some sense random. She could have chosen a 7, a 12, and calculated the -6, okay? So seeing any one of these three numbers reveals nothing about her number 13, okay? And this is true for the other three as well, okay? We move to the next step. Now, she takes this number, the 13, and I just reorganized the numbers, -6, 12, and 7. What does she do? She holds on to the -6, okay? She gives the 12 to this one, and she gives the 7 to this one, okay? This woman learns nothing about the 13. This woman learns nothing, and the -6, she's holding it, but she also knows the 13. And all three of them do exactly the same thing, okay? They distribute the numbers to the other two parties while holding one piece. Okay. Now, let's look at what this woman does. She takes the numbers that she has, and she sums them up. And she got a 16, okay? This 16 has nothing to do with any of the three numbers. It's just a random number, because it's a sum of three random numbers from her perspective, okay? And now, all three of them do it, okay? And now they expose this value, okay? The 20, the 16, and the 5. And magic, it equals 41. Okay? So the slide at the beginning said a bit of crypto magic, but it's exactly what it is. We managed to add numbers without knowing anything about the input of any one of the parties. Any questions on this? Okay. So, as I said, I gave a very, very simple example of how to do this addition. The reason it definitely delivers addition, the reason that it's not a very, very good technique is because we'll struggle with the multiplication in this case. We need to find techniques that are a little bit more of more structure, mathematical structure, in order to deliver the multiplications. And that is where the polynomials come in. You can think about it not as sharing things additively, but as sharing things over a polynomial. Okay. So this gives us the addition. And as I said, we have addition. I have to provide the multiplication. I will not show you the multiplication because I can't do it in this additive form in a simple way. And the other technique is a little bit too elaborate for such a talk. Okay. So now I want to tell you a little bit about threshold signatures and how they work. And I want to do a quick digital signature tutorial. It's really quick. So in a public key crypto system, you have a secret key and you have a public key. I don't have the public key in this thing. And you sign the message with your signature, with your secret key, and the signature is verified via the public key. So how do you do this? You have the secret key stored secretly, hopefully, on your machine. And we have a signing algorithm that takes a document, takes the key, and it outputs the document signed with this little key, okay? And the signed document is a function both of the document which is being signed and of the key, so that you cannot move the signature from one document to another document. This is the properties of the digital signature scheme. So in this setting, as I said, we have a single point of failure. If somebody breaks into this machine, it will see the key. And in fact, somebody who has your key, they are you, because they can do anything using that key. So it's a very dangerous situation for something like that to happen. So what we want to do, and this is what we do in threshold cryptography, we take the key and we split it into 3 parts, okay? And these 3 parts, the way that they would work is the following. There is the client, and they have the document, and they send the document to these servers, okay? These servers will interact in order to deliver the signed document. And the signed document is going to look to the client exactly as if it was signed just by a single key. It doesn't even have to know what's happening in the belly, okay? And in fact, this is very important because I can very simply do a threshold signature key, a signature scheme. I can take 3 keys and I can say the signed document needs to be signed by these 3 keys. But this gives us a 3-fold blow-up, which we don't want to have. So what we want is that the signed document will look as if it was signed by a single key in a single location. So that's a very important property. Of course, these guys could do it very simply, right? They could reconstruct the key and sign, but we don't want that. In threshold cryptography, we want that each one of them will do a local computation, never exposing this share of the key. And this is the way threshold crypto is a subset of multiparty computation. You have to consider this as the input. And it'll keep the secret parts of the key secret. In fact, I'll show you a really simple way to do this. I didn't prepare a slide, but let's say that we have a key X. I'm a little bit fudging on everything, but let's say that the secret key is X, and a signature on a message would be M to the X, okay? This is what we want. Nothing that I'm saying here is correct, but sort of. So I'll take X and I'll share it into 3 pieces, okay? X1, X2, and X3, okay? And now I'll give P1 X1, P2 gets X2, and P3 gets X3, okay? And now you can see how these 3 servers can sign together. P1, okay, I want to say something about assumptions. I said that the signature is M to the X. Why is this even a good thing? Because we have an assumption that computing discrete logs is hard, okay? This is the computational assumption which this signature scheme is based on. So now P1 gives M to the X1. This keeps X1 secret because of my assumption of discrete log, okay? that nobody can compute x1. This guy gives m to the x2. This guy gives m to the x3. And of course, now we just multiply, which equals m to the x1 plus x2 plus x3, which equals m to the x. Okay? So we very simply, for something that is an oversimplification of a signature scheme, we managed to do a threshold scheme. It would be very nice if this was actually a signature scheme, because it has a very nice property that, in fact, they don't need to interact. Thank you. They don't need to interact. Here, they actually do need to interact in these protocols. But here, they can just publish this information, and anyone can compute the signature. So this is threshold crypto, and as I said, it's finally also, I have to tell you that when I was interviewing for a job at IBM in 1996, my interview talk was about threshold signatures. And I think that really only now with the surge of cryptocurrencies are people really thinking about these technologies. Okay, so it's been a long road, and it's been a very exciting road and a very, very interesting road. And I really think that if these are the things that interest you, there's really a lot of work to be done now, especially when we may find maybe in 20 years I'll come and give a senior lecture talk, and it'll still be about how we're hoping that multi-party computations will be adopted. But hopefully we are on the verge of these things. And I do want to say that I had taken leave from UPenn to go to AWS, and not with the intention of publishing more papers and doing more of what I've always done, but really with the hope of introducing these techniques into things that companies use, and by that, improving their privacy. Threshold crypto also improves security, because you have this issue that you need to break into, you eliminate the single point of failure. And I'm really, really hoping at this point that we will manage to get some of these techniques deployed by Amazon. I think that if we do, it'll probably be the most used threshold systems and MPC systems, because I'm sure you've all used Amazon. And thank you. And so I really think that this is a huge opportunity to try and get these systems deployed and used, and because I do believe in it and I think it's great, but it's challenging, because when you go to people in these companies, you have to explain to them really what's the added value that you're giving. Why is this going to make a difference? And we believe in it, but there's also, and we can sell it to another researcher, but selling it to people who are in practice and who are building the systems and who lose sleep at night because they think the system might crash, and then millions of people are quite upset, there's a road ahead. And, but it's very, very interesting. It forces us to think differently about the problems, about how we approach them, about how we present them. And I was giving this example to Douglas. When we write our threshold papers, we talk about why there's an attacker that might come and attack the system, and then if it breaks, if there's a single point of failure, it'll see all the keys. Let's say we're talking about threshold. But it turns out that when you go inside and you speak about these things, they're not worried about an attacker in some way, but they are concerned that something might happen inadvertently. Somebody goes to service the machine and dumps the memory. These things could happen. And you have to understand that these things help against that as well. But you have to understand that you have to come and tell the story in the way that touches and is relevant to the issues that are concerning to people in the real world. So, thank you very much.
Thank you very much, Tal. Do you have any questions?
Thank you for a great talk. So I just taught MPC secret sharing in my class recently. And one of the questions, this is a systems class, and students were very practical oriented, and they were like, how good is the non-colluding assumption? So even if we think that secrets are shared across different cloud providers, how good is the non-colluding assumption? And I, as a researcher, I'm very fascinated by this, but I couldn't really answer the question. And so with your experience at Amazon, I was curious what your thoughts are on that.
Okay. So first of all, clearly you have very good students. Sometimes these answers are not simple, they're complex. But one answer would be, okay, let's say that you are running a certification authority that is signing people's key, and you want to do a threshold thing, and you want to assume that these signatures are not being forged. You run your, each party is running secure hardware, independent secure hardware. You have to guarantee something to say that they're not colluding. So that could be a solution, that you say, a Nitro Enclave or Azure or something like that. You have to deploy it in a way that you actually guarantee the non-colluding. These secure hardwares only enable you to write the code that was put on them. You can't run other code. And the things that they output are also prescribed. So they'll never get out their input or something like that. So it has to be some form of question like that. Another answer would be, in my example with the bank, okay? That there were all these clients that you wanted to compute the sum somehow. Maybe the parties they're self-motivated not to collude, because maybe it's their credit card number that will be exposed or something like that. There could be some external mechanisms that motivate parties not to collude. You have to think about your setting, about your protocol, about your model.
Any other questions? So I was just wondering if you could talk a little bit about you spoke about how there's bespoke techniques, custom protocols for problems, and there's general techniques. And general techniques are getting better, but also maybe we're building up building blocks from the bespoke techniques that could be applied to more problems. So where do you think we're going to end up on that spectrum? Will we always be building bespoke techniques, or will general techniques eventually be good enough?
It's a very, very good question, which I would love to know the answer to. But if I had to guess, I would say that it'll be definitely never reach the fully tailored solutions. Those will never be general solutions, or even those building block solutions will never be as good as that. And I do think that there will be a gap between the building blocks and the general solutions. That is, we won't get to a point the general solutions are so good that they are, though there are papers that show how to do AES really, really fast, and they're general solutions for addition and multiplications. They work really, really fast. I don't know. I don't know.
But cryptographers will be employed for a while.
I definitely think that this is true. I think that students now are all going to machine learning because, I don't know, it excites the mind. But I think that even systems like that need security. And cryptography, of course, is a part of it. I don't see cryptographers going out of business.
Any further questions?
Yes, there's a question.
Thank you. Thank you for wonderful talk. Okay. So because you mentioned for the Bitcoin, like the security keys, then you try to using multi-party computation techniques. But who will do this? Because the Bitcoin system is the decentralized system. So which means in the system, those like miners or customs. So right now is the consumer or customs the private key, right? So who does this?
Okay.
Yeah.
So Bitcoin itself is a distributed system where the miners work and so on, and other systems, proof of stake, like Ethereum and so on, all these different techniques exist. This method for securing the key is for your private wallet. You mined coins or you bought coins somewhere. These coins are associated with a public key, with this public key of your wallet, okay? In order, you bought Bitcoin at $10, you were very lucky, and now this morning you woke up and you said, wow, you know, I am quitting the job here and here I go. And you need to sign, in order to sell Bitcoins, you use this secret key. It's your key. It's not a distributed key. But you will take this key and you will store it in some service that offers, like, there's a company, Fireblocks, they do for industrials, but a company that splits the key on your behalf. You hold maybe one share, maybe you're P1, and then there are P2 and P3. So it's independent of how the blockchain works, whether it's a proof of work, a proof of stake, a proof of space, doesn't matter. It's for your individual wallet.
Yeah, so basically you still, for example, Filecoin, then basically you still need to send your private key to Filecoin.
To Fireblocks, yes, and they'll distribute, yes, exactly.
Yeah. So still, like a user himself, he has to respond for their action.
Say again?
You know, that's the problem. That's what, because as the user themselves, they have to respond. For example, they need to send their wallet key to the Filecoin. For example, we said Filecoin.
Okay.
And you have some other companies, even in Toronto, they also provide such a service.
Okay. I think this is what you're asking, which is a very good question. Let's say that this is my secret key, the X, and I split it somehow. How do I authenticate to these parties that they should generate the secret? So this is a very important question, and there are works on this front also of how do you authenticate. It can't be, again, with a secret key, because then we're sort of in a circular problem. So these things have to be done via some passwords that you keep locally that hopefully you don't forget. And you authenticate somehow with these passwords, with some...
Back to the password.
Yeah. So you authenticate with these passwords and some sophisticated protocol, but it is an issue of how do you give the instruction to sign. And it has to be designed, and I just didn't touch on this part.
Thank you.
Wonderful. So my question is similar like Douglas' one. I think, as you mentioned, the threshold cryptography has been existing for many years. And I wonder what is the state of art of cryptography research? Like what are people doing these days? Not talking about publishing papers, but contributing to this academic field. Is it falling into something like you need to find a scenario and find a problem for like industry use, and you try to use the generic algorithms, basic ideas like Shamir secret sharing to do the optimization for this type of specific problem that you have. Is that correct?
So, as I said, threshold crypto is doing a little bit better than MPC, and MPC techniques definitely use Shamir secret sharing, and threshold sometimes also use it. Instead of doing an additive sharing, it's not important if you don't know, they could be doing a Shamir secret sharing here. But the fact of the matter is that actual implementations today do 2 out of 3, 3 out of 3. They're really not doing generic solutions. And for the cryptocurrency world, it really is just the sharing of this key. So the problem that you said you need to find the problem is straightforward there. It's just the signing key for the wallet. In Amazon, when we look at all kinds of things, and we don't look just at threshold signatures. There are other functions that you can thresholdize. And we are actually looking at specific designs of what is out there and trying to figure out what to do. I don't know if we will write papers. I don't know if it'll be interesting enough to write actual academic papers, but it will be super exciting if it's implemented. And we too are going for the simplest, 2 out of 3, no general anything. Actually doing and fixing the parameters and the functions that we are computing and how we are computing and how they communicate and so on to optimize as much as we can. So
if your problem, your scenario changes, your algorithm needs to be adjusted by the cryptographers too, right?
100% at this point. Douglas was also asking about the generic solutions versus the tailored solutions. I feel that at this point in time, we still need to prove that these techniques work. We need to give special solutions that will work and people will use. Later, when we're resting on our laurels and, Amazon is completely MPC'd and thresholdized, then maybe we can start doing things that are maybe less efficient and more general, but we're not there. I mean, I think we really are at the stage of this technology that we need our big break, and we haven't had it yet. Maybe cryptocurrencies with threshold, with the signing keys for the wallet, they're having a little bit of it, but it's not widespread either. I don't know. I'm sure people here have cryptocurrencies. I'm sure none of them has thresholdized their keys, including me. So.
I see. Thank you.
All right, well, please join me in thanking Tal for her lecture.